Hello everyone, my name is Camille and I am a researcher at Toyota Motor Corporation. This session is called RAMN for Resistant Automotive Miniature Network, and I will talk about a small platform that we developed for studying and researching automotive systems. If you were curious about automotive systems but never knew where to get started, this could be of interest to you. And if you're already good with automotive security, this may still help you with your research. It's called miniature because it has the size of a credit card, and it's called resistant because it was designed to resist harsh environments, just like real automotive electronics. And I will explain what makes automotive electronics different from other kinds of electronics. But first, here is a quick demo. RAMN is an inexpensive automotive testbed, which has the size of a credit card. RAMN emulates an automotive network of 4 electronic control units connected over a CAN bus. You can add sensors and actuators to simulate the controls of a car. You can connect the testbed over USB, and it will be recognized as a standard USB to CAN adapter, so you do not need any other equipment to start experimenting with automotive systems. You can add features as you like by plugging in additional boards. You can connect it to Carla, a popular open-source autonomous driving simulator, and simulate the network of a self-driving vehicle while staying in the safety of your home. It is close to be automotive grade, which is something I will explain in detail later. Finally, it is open source, so you should be able to make one yourself. Let me explain why this is an interesting testbed and how it is different from currently available solutions. To do so, I must first talk about what automotive grade means and why that matters for security. Then I will show you all the design details and demonstrations and explain what I would like to achieve with this project. I must first mention the importance of automotive security and the role of testbeds. If this is not your first automotive security talk, please bear with me for the next few slides. Even if you are not interested in cars, you have probably heard the news. Researchers have demonstrated several times that connected cars could be remotely hijacked. Many critical vulnerabilities have been reported on several models from different manufacturers, and people are concerned about the security of the cars that they are driving. Cars have always been the target of many crimes, including theft, fraud, counterfeiting, bypassing regulations, etc. And you might be thinking, well, I don't drive a car, so it's not my problem. But compromised vehicles are often used to achieve worse crimes. As stated by Interpol on their website, stolen vehicles are often used to carry out other criminal activities, ranging from drug trafficking, arms dealing, people smuggling, and international terrorism. An insecure car is a problem that can impact everyone. The stakes are high, but securing cars is not an easy task. A car is made of hundreds of computing units, which are made by different companies, and are running thousands of lines of code. There are many elements required to ensure that there is no vulnerability in a car. 3 of those elements are the presence of many automotive security experts across companies, good cooperation between them, and efficient tools at their disposal. One of the many tools that automotive security researchers need is a testbed. Automotive networks are a collection of ECUs, which stands for Electronic Control Units. Each ECU has one or several functions. For example, the airbag ECU is in charge of detecting a shock and triggering the airbag. The ECUs communicate with each other using a technology qualified for automotive use. There are many of them, and the most common one is a CAN bus. CAN-FD is a recent evolution that increases the maximum data rate of the CAN bus. Neither CAN nor CAN-FD has built-in security features. It is up to the layers above to ensure security. If you want to experiment with an automotive network, you have several options. The first one is to use a real car. The obvious advantage is that you get to experiment with an actual network of ECUs. but the drawbacks are that it is expensive, that you are unlikely to have access to the source code and specifications, and most of all, that it is dangerous to tamper with the car. As a consequence, many researchers decide to use a testbed instead of a real car. You can often find cool testbeds made from scrap parts at security conferences. They usually are fun to play with, and they involve actual ECUs, so they are representative of a real automotive network. However, they are not easily reproducible. They require a lot of resources to build, so they are out of reach for beginners. And again, those testbeds use ECUs for which the source code and specifications are not made public. Because of those drawbacks, researchers in academia usually do not use such testbeds. Instead, they invent testbeds that are easy to reproduce, and for which they have the source code and specifications. Many research papers are making use of Arduinos and Raspberry Pis. Such testbeds are not really appealing to newcomers in automotive systems, but more importantly, they are not built with actual ECUs, which is a problem I will talk in detail later. The last option is to use a professional testbed, such as Pasta. Pasta is an automotive testbed that was presented at Black Hat Europe in 2018. It was developed by researchers at Toyota, who are also authors of this research. The advantages of Pasta is that its specifications and source code are open. It is adaptable, so it can be used for a wide range of research, and it is portable, so it is easy to share between researchers. And also, it's fun, so it is a nice way to get people interested in automotive security. The drawbacks are that Pasta is expensive, and that similarly to academic testbeds, it is not built with automotive-grade technologies. All testbeds have their advantages and drawbacks. I personally see two problems with automotive testbeds that I would like to address. The first problem is that they usually have a high entry barrier. Either you need to pay a lot of money to buy a testbed, or you need to invest a lot of resources to build one. As a consequence, there is less freedom for researchers. If there is only one expensive testbed, they will need to share it, they will not be able to modify it, and they will have to worry about not breaking it. Another consequence is that less people start learning automotive systems because they cannot afford to. This results in less talents who are knowledgeable about automotive security. In comparison, there are many ways to get started in other fields of study. If you want to learn electronics, you can buy an Arduino. If you want to learn about embedded Linux, you can buy a Raspberry Pi. If you want to learn AI, you can buy a Google Coral or NVIDIA Jetson Nano. They all have a low cost and a supporting community, which means many people get involved every year. There should be the same thing for automotive systems. The second problem I want to address is that most testbeds are not automotive grade. Let me explain what automotive grade means and why it matters for security. And I know it might not seem like the most interesting topic at a security conference, but I will try to keep it simple and interesting. The first question that needs to be answered is, why do we need different grades of electronics? Customers have different expectations for different products. For example, regular smartphones are designed to operate between 0 and 35 degrees Celsius, and it seems that most customers are fine with that. Smartphone manufacturers could extend the operating temperature range if they wanted to, but that would likely result in a higher price and lower performances. Most customers would not be happy with that decision, since they would perceive no benefit. Electronic components are designed to match the expectations of the customer base, not less because the customer will not be satisfied, and not more because it leads to higher prices. Electronic components typically fall into one of these four grades: commercial grade, industrial grade, automotive grade, military and aerospace grade. Automotive-grade components are different from other components because they need to operate in very harsh environments. They need to be safe and reliable. They need to have a long life expectancy and be available for as long as they are needed by customers. And they are purchased in high volumes. Let me elaborate on the environment. As I said earlier, smartphones are designed to operate from 0 to 35 degrees Celsius, but they can resist a wider range when not in use. The storing temperature of a smartphone is -20 to 45 degrees Celsius. That is still not enough to survive in some conditions. For example, in the instruction manual of most smartphones, it is explicitly said not to store the device in a parked car. Now think about the ECUs. Not only do they need to be stored, they also need to operate at those temperatures. And minus 20 degrees to 45 degrees Celsius is still far from the worst they will experience. ECUs in the engine compartment are typically designed to operate at a temperature range of minus 40 to 150 degrees Celsius. That is already a hard challenge. But there is even more. They also need to resist high humidity, salt sprays, corrosive atmospheric gases, dust, vibrations, shocks, unstable power supply, electrostatic discharges, electromagnetic noise, and last but not least, people. And when subjected to such a harsh environment, many things could go wrong in an ECU. You probably know about corrosion. What you may not know is a myriad of other physical phenomena that could happen. Solder cracks, intermetallic growth, whiskers, dendrites, electromigration, etc. Whiskers are metal growing out of electrical components. Dendrites are metal leaving the plus side to go to the minus side. Many of those phenomena may result in a dangerous short circuit. Automotive-grade components are designed with countermeasures for those phenomena. The Automotive Electronics Council has created several standards for qualifying electronic components to be used in an automotive environment. 4 grades are defined, depending on where the component is used. Grade 0 has the most stringent requirements, with a temperature range of minus 40 to 150 degrees Celsius. It is meant mainly for components in the engine compartment. You may be wondering which one of automotive and aerospace has the harshest requirements. There are different problems in space. There are more radiations, components are more susceptible to grow thin whiskers, etc. They also have a different temperature range. Aerospace components must resist lower temperatures, as low as minus 55 degrees Celsius. But the highest temperature is 125 degrees Celsius, lower than grade 0 of the Automotive Electronics Council. Since requirements are not that different, aerospace and automotive components might be compatible, but there is no guarantee. So sending a car into space is a good publicity stunt, but it is probably not recommended. Also, I am not sure this is the scenario that smartphone engineers envision when they tell the users not to leave the device in a car. But it is unlikely that commercial-grade components can be used in space. The second point I want to address is reliability and safety requirements. The consequences of a random failure are not the same for all grades. For commercial grade, in many cases, the customer is not in danger. If the manufacturer provides good service, customer will probably forgive them or even like them more. For industrial customers, you cannot just offer them a replacement and hope they will forgive you. Stopping a line in a factory can cost thousands of dollars per minute. For automotive grade, if a component is in charge of a critical function such as braking, it is likely its failure will lead to people being physically harmed. Someone will need to take responsibility for it. With hardware, failures always happen. You may not know when they happen, you may not know why they happen, but you know that they will happen. You can try to predict the failure rate with different methods, or you can run accelerated tests and use statistics. Reputable manufacturers will make it easy for you to access their failure rate data. One key metric you often see is the FIT, failures in time. It is the number of failures expected per billion device hours. For reference, the probability of being struck by lightning is equivalent to 0.23 FIT. The probabilities are low, but remember that there are millions of cars with thousands of components that are operating for thousands of hours. So those risks cannot be ignored. The impact of every possible failure must be considered. Let us use a simple example. It is common in electronics to add a capacitor between the power supply and the ground. If the capacitor fails, it may result in a power supply short circuit. And not only could that result in a fire hazard, but it will prevent the ECU from functioning. And if the ECU is critical for the safety of the driver, then this can have catastrophic consequences. This is what is called a SPF, for single point fault. And it is one of the many things that are typically avoided in ECUs. One way you could remove a single point fault is by adding a detection mechanism. If you can detect the failure, then you may prevent catastrophic consequences. But there is still a chance that the detecting mechanism fails, so it is not a perfect countermeasure. The second option is to use redundancy. With two capacitors in series, one can be short-circuited without leading to immediate danger. But this costs money, and there is still a chance that both capacitors fail at the same time, so it is still not a perfect countermeasure. So you may be wondering, if the ECU is very critical, why not do this? Or even this? And remember that right now I am only talking about one component. There are thousands of components in a car. Where do you set the bar for the probability of a catastrophic event? How safe is safe enough? To answer this question, the automotive industry has developed standards. ISO 26262 is the most famous one, and it covers much more than what I just talked about. It defines 4 safety levels for ECUs, called Automotive Safety Integrity Level, or ASIL for short. For reference, here are the metrics I mentioned earlier required for each level. Another standard you can find is ISO 16949, which features many funny words such as PPAP. It is mainly used to ensure good communication within the industry. Because if the factory makes a mistake, for example by soldering the wrong components, a safe design is not safe anymore. Software is also covered by ISO 26262. Software does not randomly fail, but random transient failures in hardware, such as bit flips induced by cosmic rays, can happen. Again, the hardware will use redundancy to mitigate such failures, for example by using two CPUs executing the exact same code and comparing the outputs, or by using ECC memory, which is a kind of redundant memory designed to detect and correct random bit flips. Software still can fail because of bugs. To avoid bugs, ISO 26262 also mandates the use of known automotive software best practices. One of the most important best practices is the use of safe coding guidelines. MISRA-C is a set of coding rules often used in ECU development, and is not very different from the secure coding guidelines of CERT-C. There are also other standards, such as Automotive SPICE, which is about the project management of automotive software. Now let's see how all that can impact the security level of ECUs. First, safety and reliability constraints limit the security countermeasures that developers can take. You could encrypt the CAN bus, you could permanently disable the debug ports, you could obfuscate the firmware, but important ECUs may require investigations if problems are reported, and those countermeasures could hinder the investigations. Safety and reliability measures usually make things harder for attackers, but they are not proper security countermeasures. It has been shown that ECC memory can still be susceptible to malicious bit flips, and that microcontrollers used in critical ECUs can also be susceptible to glitching attacks. The ECUs need to operate at high temperatures, and it has been shown by researchers that the higher the temperature, the higher the probability for a glitch to succeed. And by high temperatures, the researchers meant something like 60 or 100 degrees Celsius. Also, the age of a microcontroller seems to impact its resistance to side-channel analysis, although in that case, the risk seems to become lower. When developing automotive security technologies, it is not enough to demonstrate that they work in a specific setting. A new technology must demonstrate that it is reliable on millions of cars, which all have different hardware characteristics because of manufacturing tolerances. It must prove that it works across a wide temperature range, and that it will still work after 10 years. And it is hard to ensure that security countermeasures work for every possible scenario. So when evaluating a technology, during a penetration testing for example, it is wiser to look for exploits in the worst conditions, such as the highest and lowest temperatures, or when a fail-safe mechanism is engaged. So for both the attacking and defending side, automotive grade makes a difference. So automotive testbeds should be automotive grade. Now back to testbeds. The two problems I had with available automotive testbeds were requiring high investment and not being automotive grade. So I wanted to try and design a testbed that could address both issues. Let me introduce that testbed to you. I wanted to design a testbed that would require low investment, which means concretely inexpensive and fun and easy to get started with. This is to make sure that it could be useful to everyone, not only those who are already good at hacking automotive systems. I wanted to make sure that research and education would be easily accessible to those who do not have automotive security skills, or who are not even sure that they are interested in automotive systems to begin with. But also, I did not want to just build a shiny toy. I wanted to design something that would be as representative as it can of real automotive technologies. As I explained earlier, this means that the testbed would have to be automotive grade. Unfortunately, as of today, I do not think it is possible to have something that is both 100% automotive and open source at the same time. So I had to make some compromises that I will explain later. For the design, I had two major influences. The first influence is from all the popular education and research tools that are available nowadays, such as Arduino and Raspberry Pi. They are really great tools, and what I like the most about them is that you do not need to learn something before you get started. You get started, and then you learn something. They have a really low entry barrier, and as unoriginal as it may be, I wanted something that was not too different, which meant for me just a PCB with more or less the size of a credit card. The second influence is from security conference badges. People in the security community love them. Some are even addicted to them. They are part of the hacking culture, and they show you can make something really fun with only one PCB. I think a lot of people buy badges so they can learn something while having fun. So I wanted a testbed that would also give a similar experience. Keeping the board small and simple was the first constraint I set. Size of a credit card, powered over USB. I also added constraints of having only 2 layers with large track spacing. If you're not familiar with PCB manufacturing, you should just know that those are factors that have an impact on how easy it is to fabricate the PCB, and therefore have an impact on the price if you order one. I added the constraint of only using easy-to-solder components, because I wanted to make sure the board could be assembled by beginners in electronics. You should also know that those constraints are very common in the automotive industry, not so much for the cost, but for reliability and safety reasons. PCBs like this are easier to inspect visually and are known to be more reliable. Next, I had to decide how many ECUs I wanted and how they should communicate. Almost all the testbeds that I have seen have less than 4 ECUs, and they are communicating over CAN. In most cases, the testbeds look like this. 4 ECUs, 1 CAN bus. I am not going to argue with that. And the good news is that even with the constraints I stated earlier, that should fit on the size of a credit card. And with recent microcontrollers, you can even update from CAN to CAN-FD. So I came up with this. 4 ECUs, 1 CAN or CAN-FD bus, inexpensive and easy to build. That was good enough for my initial goal. Now I just needed a name. I thought, what's a cheap version of pasta that students like to make themselves? And the obvious answer was RAMN. All components have visible pins and are not too small, even the capacitors. They are also all located on the same side of the board, so the testbed can be soldered with beginner skills. It's not the easiest board out there, but it's not too hard. Because the testbed is inexpensive and easy to assemble, it is possible to make many boards, which can be used to evaluate the impact of manufacturing tolerances. Also, it's possible to permanently modify them or perform evaluations in harsh conditions where they are very likely to break. It will not cost a lot compared to other testbeds. The block diagram of the testbed looks like this. There are 4 ECUs, including 1 ECU that is connected to the USB port. That ECU can also access the power supply and boot mode pins of the other ECUs, so it can turn them on and off, and can also reprogram them. The ECUs have no actuator or sensor. Instead, they have a pin socket, so that they can be added separately. They are all connected to a common CAN or CAN-FD bus, which can be physically accessed from a terminal block. So this board is enough to emulate a network of 4 ECUs communicating over a CAN bus. It's a real network, but as it is, it's still not really fun. So I wanted to add some elements to try to make it more like a badge, to make the testbed more appealing to people who have never considered learning about automotive systems. The ECUs have expansion sockets to add sensors, actuators, and other features. I developed several expansion boards to illustrate that. I did not keep the automotive-grade constraint for those boards, because they're not absolutely required for emulating an ECU network. The first one is a screen expansion, compatible with several inexpensive screens that can be ordered on the internet. The second one is a board that features a steering wheel and that is meant to emulate the functions of an ECU located in the chassis domain. It also features other buttons, for example to emulate the side brake. The third one is a board that emulates the brake and accelerator pedals, as well as a gear shift. It is meant to emulate the functions of an ECU in the powertrain domain of an automotive network. And the fourth one is a board to emulate the functions of an ECU in the body domain. It has a key lock and some LEDs to look like a dashboard. And when you assemble them all, the testbed looks like this. And I thought, there are many pins available, so why not stack the expansion boards like people stack Arduino shields? So I designed 4 more expansion boards. I created an expansion to connect a JTAG debugger and to access all signals with clip-on probes. It makes it possible to debug each ECU individually. I created an expansion for external memories for both SOIC8 and SOIC16 packages, which can provide up to 1 gigabit in extra storage. I used it to experiment with different kinds of memory technologies, such as Flash NAND, Flash NOR, EEPROM, NVS RAM, and FRAM, and so on. I created expansion boards for TPM chips as well, both version 1.2 and 2.0, with either SPI or I2C interface. And finally, I created an expansion board to easily connect the testbed to the popular side channel analysis and glitching tool Chip Whisperer. The expansion boards are mostly compatible with each other, so you can just add and remove features to the testbed as you want. All PCBs are designed using KiCad, which is an open source tool that does everything from schematics creation to PCB layout design. It can even generate nice 3D views. As a result, it is easy to design new boards or modify existing ones. Another one of the initial goals was to enable people to get started quickly with learning automotive skills. But most people don't have a CAN adapter at home. They also do not have a JTAG programmer to program the memory of each microcontroller. And forcing them to buy one is forcing them to make a new investment, which I wanted to avoid. So I wrote a firmware for the ECU connected to USB to use it as a standard CAN adapter. It's compatible with both Windows and Linux, and you can even use it as a standard Linux interface. Here is a quick demo. If you connect RAMN over USB to Linux, it will be recognized as a serial port. You can turn that serial port into a network interface using the SLCAN daemon. Then you can use the tools of your choice to observe the CAN traffic of RAMN. Here, I am showing the popular can dump and can sniffer tools. For programming the ECUs, I wrote a tool in Python that implements the CAN boot protocol available in the microcontroller's ROM. Here is a demo. You can use the reprogramming tools to display information about the ECU microcontrollers. You can read out the flash memory, for example, to dump the firmware of the ECUs. You can activate security features, such as memory readout protection, and observe the effects they have on dumping the firmware. And of course, you can reprogram the ECUs. Another thing I wanted to facilitate was the connection to tools usually used by hardware hackers. The testbed features various technologies commonly seen in hardware, such as SPI, I2C, shift registers, analog inputs, and so on. I added many clip-on probes so that it is easy to connect an oscilloscope and have a look at analog signals, or connect a logic analyzer and have a look at digital signals. And finally, I wanted to integrate the testbed in a driving simulator to expand its possibilities beyond hardware. Fortunately, talented people already wrote one called Carla, which they released as open source. If you are not familiar with the project, Carla is an open source simulator for autonomous driving research. It is based on Unreal Engine and you can experiment with it using a Python API. It comes with an example self-driving algorithm, so you just need to download Carla and launch a script to get started with autonomous driving research. Carla is a simulator, so by default it is software only. I implemented a new API so that the vehicle controls of Carla will not be applied by software, but in hardware by the testbed. This is done in closed loop, so values that only exist in the virtual world, such as vehicle speed, are also visible on the canvas. Here, I am showing a demonstration of what it looks like when running Carla on a computer. You can choose a vehicle and the conditions in which it needs to drive, and Carla will simulate them. In this case, I chose a truck and an empty city during daytime. An autonomous driving algorithm is controlling the car, and everything happens in the computer's software. It is possible to connect RAMN to control the car manually. Here, I slightly press the accelerator and release the handbrake. Now, the car is being controlled by the sensors on the board. It can turn, accelerate, and brake. RAMN can also be used together with a self-driving algorithm. Here, it is waiting for me to release the handbrake manually. Now, the vehicle is driving itself, but RAMN still has control over the vehicle. You can see the stop lamp on RAMN lighting up as the vehicle stops at a red traffic light. Again, because RAMN is in charge of the controls, you can brake anytime by pushing the brake pedal. This also means that a compromised sensor can have an effect on the self-driving vehicle. Here, I am demonstrating what it looks like when the steering wheel is compromised. In all cases, RAMN is emulating 4 ECUs communicating over a CAN bus. If you connect a CAN adapter, you can observe the network traffic on the CAN bus. Here, you can see how the acceleration of the vehicle impacts some fields, highlighted in red. This also means that sending malicious CAN messages can have an impact on the vehicle. Here, I am sending braking commands over CAN. If you can think of innovative security countermeasures, you could reprogram the ECUs or connect a new ECU of your design to the terminal block. Then you could develop and evaluate those countermeasures using RAMN. This was the last demonstration. I will post more online. Before I talk about the firmware, I need to talk about automotive grade again. I wanted the main board to be fully automotive grade. Nowadays, many automotive grade electronic components are publicly available for purchase in small quantities. Unfortunately, automotive microcontrollers are not publicly available and require to sign NDAs to purchase, and you need to commit to buy thousands of units. The software toolchain is also expensive and closed source. There was the same problem with Pasta, and with RAMN, we had to compromise again. The good news is that you can find publicly available microcontrollers that are close to automotive grade. The testbed is compatible with both the STM32L4 series and its recent evolution, the STM32L5 series. Those microcontrollers offer features typical of automotive microcontrollers, such as ECC memory, and they can resist temperatures from -40 to 125 degrees Celsius. It is still not AEC grade 0, but it is a good start. The microcontrollers feature capabilities useful for researching automotive security: a true random number generator, an optional AES engine, trust zone, secure boot, secure reprogramming, and so on. And of course, they have a CAN or CANFD controller. The firmware is based on the STM32 HAL library and FreeRTOS, which are both open source and compliant with MISRA-C. FreeRTOS is not compliant with automotive standards such as ISO 26262, but there is a variant called SafeRTOS, which is compliant. Of course, that variant is not free, but you can read about the differences and know exactly what is missing in FreeRTOS. Here is a summary of the differences between RAMN and Pasta. In terms of CPU performances, there is no difference, but RAMN has less flash memory than Pasta if you do not use a memory expansion. RAMN has a higher operating temperature range, but neither Pasta nor RAMN is automotive grade. RAMN is much less expensive than Pasta, but it is not a replacement to Pasta. Pasta is designed and maintained by a team of experimented professionals. RAMN is not. However, I do hope people will be interested in building a community around it. RAMN and Pasta are different tools, but they have the same philosophy. They also have the same CAN message specifications. The main merits of RAMN are that it is close to automotive-grade specifications, so that you can develop and evaluate technologies in conditions similar to those of real ECUs. It is inexpensive, so you can make a lot of them. which means you do not need to share your testbed with other researchers. You do not need to worry about breaking your testbed, and you can evaluate the impact of manufacturing tolerances. It is also easy to get started with RAMN for beginners in electronics and embedded software. So hopefully, it will lead to many people getting interested in automotive systems. RAMN has some limitations. For example, there is only one CAN bus, and there is no 12 volts power supply, like in PASTA or real automotive systems. I do not think that those limitations are a big problem, as they could be addressed with dedicated boards. However, there is one limitation that I want to get rid of. The testbed is not 100% automotive grade. It is doing well in terms of operating temperature range and basic redundancy features such as ECC memory, but it is still not automotive grade, and that is to me quite unsatisfying. And unfortunately, it is not something I can fix just by making more stuff. So that brings me to the last part of the presentation, which is explaining what I would like to achieve with such a testbed. I understand why the automotive industry is so closed. There are very good reasons for that. It takes a lot of resources, money, time, skills, to develop automotive-grade hardware and software. But it is hard to get people involved in automotive security when it requires an NDA to even get started. New standards are being introduced in the automotive industry to hold cybersecurity to the same level as safety and reliability. ISO 21434 is a new standard that is being introduced to guarantee the cybersecurity level of automotive systems, and it will help a lot. But standards do not solve everything. Even with the experience in safety and reliability that manufacturers have accumulated over the years, modern cars can still have safety and reliability issues. They might come from scenarios no one imagined before, or other reasons. It is not wise to expect things to be different for security. The more automotive security experts there are, the more we will have solutions. This testbed aims to promote more openness in the automotive industry, to get more people interested in automotive systems, to facilitate education on automotive security and possibly on other topics such as safety and reliability, and to facilitate research on ECU networks for people who are already experts in automotive systems. But RAMN is not a car hacking tool. The CAN bus is terminated on the PCB, so you cannot connect it to your car. It is not a replacement for a CAN adapter. It is a replacement for your car. RAMN is also not an endorsement of car hacking. It might be illegal in your country, and many car manufacturers do not have a bug bounty program, including Toyota, so please be careful. In the future, RAMN could be used as a more formal platform for education, evaluation of automotive security skills, bug bounties, and CTF. Those are some ideas I would like to explore. If you like the project, you may be wondering how you can get one. Right now, we are still focusing on improving the quality of the design files. We want to make sure they are not ambiguous, so it is easy to order one from PCB fabrication services. If you are comfortable with electronics, and if you do not mind minor bugs and want a RAMN now, feel free to contact us. Thank you for listening to this presentation. Feedback from the community is always appreciated, so if you like the project and maybe even want to contribute, please let us know. If you have questions, I will be on Discord and Brella for the rest of the event. Thank you.